Good morning, students. In today's session, we are going to deal with the speed of transverse wave and speed of longitudinal wave in various media. Okay, first of all, let us come to the transverse wave. Speed of transverse wave in a stretched string. Speed of transverse wave in a stretched string. So, stretched string we already studied that a man is just fixing a rope on one end and he is keeping the other end, and then when he pull it, wave will be produced. So, that is a transverse wave in a stretched string. Or guitar, think about the string of a guitar, when we pluck one end, the waves are produced. So, the speed of transverse wave in a stretched string depend on two factors. The first factor is tension of the string, and second factor is mass per unit length, denoted as mu. So, speed of transverse wave in a stretched string depend on two factors. The first one is tension and second one is mass per unit length, mu. So, I will be writing like this: V is equal to root of T by mu, and mu is equal to mass per unit length. Therefore, I can write V as root of T by mass per unit length. So, V is equal to root of T L by m. This is the velocity of transverse wave in a stretched string. We do not have the derivations to study, we have only the equations. So, please note down. Now, next one, speed of transverse wave in a solid. Speed of transverse wave in a solid. So, that depend upon two factors, the rigidity modulus and the density. So, I can write like this: depends on two factors, rigidity modulus of elasticity that is capital G, and second is density of the material, density of the medium. So, here it is the solid medium, so density of the solid and rigidity modulus of the solid. So, V is equal to root of G by rho, rho is density. Here also we have only equations to study. So, V is equal to root of G by rho. Now, next one, speed of longitudinal wave. In a solid rod. So, transverse wave we studied two things. Now, we are doing with the longitudinal wave through a solid rod. So, that depend upon two factors, Young's modulus and density. So, I will write the two factors are Young's modulus denoted by Y and density of the medium denoted by rho. So, the equation will be V is equal to root of y by rho. V is equal to root of y by rho. Now, speed of longitudinal wave through liquid or gas. Fourth one. Speed of longitudinal wave through a liquid or a gas. Longitudinal wave passes, when longitudinal wave passes through liquid or gas, it depends upon two factors: the bulk modulus of elasticity and the density of the medium. Through solid, it was Young's modulus. Through liquid or gas, it is bulk modulus. So, the two factors are bulk modulus, which is B, and density of the medium denoted by rho. So, V is equal to root of B by rho. This is the velocity of the longitudinal wave through liquid or gas. Newton's formula for speed of sound in gas. Newton told that when the sound propagates through air, when sound propagates through gaseous medium, the process is isothermal. You know what is meant by isothermal? Isothermal means the temperature remains constant. So, Newton told when sound propagates through gas, the process is isothermal. So, there is no temperature change. So, he wrote like this. Velocity of sound will be root of V isothermal by rho, and by his we don't have the derivations to study. By his calculations, he got B isothermal is equal to the pressure. Therefore, he wrote V is equal to root of P by rho. This was the expression that he modified. The original equation is B by rho, and since he told the process is isothermal, he just wrote B isothermal by rho. So, V is equal to P by rho. B isothermal is found to be P, and it is P by rho. And when he calculated the velocity at STP, standard temperature and pressure, at STP, he got the pressure is 1.013 into 10 raised to 5, and the density is 1.293. When he calculated this, he got the answer as approximately 280 meter per second. But the real speed of sound is 331 meter per second. So, there is a 15% error. Okay. So, the actual value of sound is actual value of V is 331 meter per second. So, he got a value which is 15% lesser than the actual value, 15% lesser than the actual value. So, there was some problem in it. So, a scientist named Laplace, he made the correction. Laplace told that when the sound propagates through air, the compressions and rarefactions are taking place very fast. And since the compressions and rarefactions are taking place very fast, there is no time to exchange the heat. As a result, the temperature cannot remain constant. The process will be adiabatic. So, according to Laplace, when sound propagates through space, sound propagates through gas, the process is adiabatic because compressions and rarefactions are taking place all of a sudden. So, Laplace did like this. Laplace did like this. The process is adiabatic. So, V is equal to B adiabatic by rho, and as per his calculation he found B adiabatic, bulk modulus in adiabatic process, as gamma into P. In kinetic theory of gases we studied gamma means ratio of specific heat. So, his equation will be V is equal to root of gamma P by rho. V is equal to root of gamma P by rho. This equation is called Newton's Laplace equation, because Newton first formulated it and then Laplace corrected it. So, this equation is called Newton's Laplace equation, and for a diatomic gas, the value of gamma is 1.4. We studied that in kinetic theory of gas. Gamma is equal to 1.4. So, he put the values. And when he calculated it, he got the answer as 331.3 meter per second. This value is in close approximation with the experimental value. So, Newton's Laplace formula is the correct one, and we are using this formula for all our calculations. Okay. Now, what will happen to the speed of sound when pressure is increased? Effect of pressure on the speed of sound. We already know V is equal to root of gamma P by rho. When pressure increases, the gases are getting compressed. Since the gas is getting compressed, density will also increase. So, when P increases, density also increase. So, P by rho is equal to a constant. Always P by rho is equal to constant. So, pressure has no effect in the speed of sound. That means if pressure increases or decreases, speed of sound remains same. Now, if I am keeping the pressure constant, and changing the density, imagine like that, I am keeping the pressure constant and changing the density. So, V is equal to root of gamma P by rho. From here I can write V proportional to 1 by root rho. I kept pressure constant. Density is only increasing. When density increases, it is coming in the denominator, right? So, the velocity will decrease. So, if density of a gas is increased, then the velocity of gas is decreased. So, for example, if I am finding the velocity of sound through hydrogen gas to the velocity of sound through oxygen gas, hydrogen gas by oxygen gas. So, V proportional to 1 by root rho. So, density of oxygen gas by density of hydrogen gas, and density is mass by volume, right? So, then it is proportional to mass. Density of oxygen is how much? 16 times density of hydrogen. So since density is proportional to mass, you know mass number of oxygen molecule is 16. Mass number of oxygen atoms mass number is 16 and hydrogen atoms mass number is 1. So that is why instead of rho O I wrote 16 rho H. So rho H and rho H can be cancelled. So root of 16:1, which is 4. That means velocity of hydrogen, velocity of sound in hydrogen is 4 times than the velocity of sound in oxygen. Therefore, we can say sound travels faster in hydrogen than oxygen. Okay. Similarly, when humidity increases, humidity is the amount of water vapor in the atmosphere. Water vapor is less denser than air. So when humidity increases, the density will decrease. So what will happen if density decreases? Velocity will increase. That means sound travels faster through moist air than in dry air. Because moist air means water vapor content is more, water vapor is less denser than air. So as density decreases, velocity will increase. Therefore, sound travels faster in moist air than in dry air. Now, what will happen to sound, the speed of sound when temperature increases? When temperature increases, there is a formula V is equal to root of gamma RT by rho. This is the relation between temperature and velocity, root of gamma RT by m. So from here, V proportional to root T. That means when temperature increases, velocity of sound also increases. So these are the factors in which the velocity of sound depends when it travels through gas. Okay, so there are derivations for all these things, but we don't have the derivations to study. These are only the basic concepts of the speed of sound. That is why I am telling this. So you need to study only this much. Okay, thank you.